Hello and welcome to session 1 of Condenser Performance Essentials with Dr. Timothy Harpster of Intech. And this is Randy Rogers. I'm General Manager of Energy Tech Magazine. And I just wanted to let you know before we get started, I want to make sure everybody knows how to ask questions. And Dr. Harpster would like you to go ahead and interrupt him at any time with any questions that you might have. So in your control panel, you'll see a questions box that you can type in your questions, and then the Intech folks will interrupt Dr. Harpster, and he'll answer the question. We have the handouts. I emailed those out to everybody, and you can also download them right from within this session in your handouts control panel. And so, Dr. Harpster, I think you can go ahead and begin.
Thanks, Randy. Can you hear me?
Yes, you bet.
Okay. All right, great. Yeah, I'm Dr. Harpster. I'm the Director of Engineering here at Intech. I also have with me Jason Reynolds. He is one of our account managers. He's our primary contact for energy tech and other outlets. I also have Colin Eckel. Colin is one of our condenser service engineers and condenser instrumentation product supervisors. And if you ever need technical assistance interpreting data or have general condenser questions, you'll probably be directed to him. And both of these gentlemen will help me moderate this webinar today. So I want to thank you all for making arrangements and setting aside time to join us on this webinar today. I also want you to know that the materials that I'll be presenting over the next 2 days are borrowed from a 2-day workshop that our company has been hosting for nearly 2 decades. Our company is very active in the heat exchanger research community. We are frequent contributors to EPRI. Our CEO, Joseph Harpster, served as the Research and Education Chairman on the ASME Heat Exchanger Subcommittee from 2009 to 2015. And so I put on this slide some of the comments from past attendees to our workshop. And our goal at this workshop and today and tomorrow at this on this webinar is to provide you with the knowledge to confidently troubleshoot condensers and understand what tools are available to help you be a more efficient condenser system owner. The major differences between this webinar and the workshop is a day of case studies. So we don't have the instrumentation case studies. We have a few in here, but that's the difference between this webinar and the workshop. Our case study session is kind of a pop quiz format. We start by teaching troubleshooting techniques, and then we show data graphs from real operating utilities, and we ask people what's the problem. So those case studies are not included in this webinar, but just so you know, they do exist, and if you ever need any help troubleshooting issues, we have materials available to help. We have a team of people that put a lot of effort into keeping this workshop, these materials up to date, and continually incorporate attendee feedback. So in summary, we believe these materials are complete, concise reference for your performance assessment needs. And having said that, we welcome your feedback. So if you feel something is missing or we can improve in some way, then please let us know. So this presentation is titled Condenser Performance Essentials, and over the next 2 days I'm going to present information to answer the questions that are essential to the understanding of a shell and tube steam surface condenser's performance. The first session is going to answer these first 3 bullets right here. Why do we care about condenser performance? So we'll talk about that first. We'll talk about what information and what resources are needed to monitor performance. And then we'll talk about how performance should be measured, how it should be valued, and how it can go wrong sometimes. And this will be review for those of you that have been condenser system owners for years. But for those of you that are new system owners, this is going to be information that will be absolutely essential for all your performance analysis efforts. Now, the second session that I'll present tomorrow, same time tomorrow, will be valuable to experienced condenser owners. For those of you that find today's sessions too basic, I promise you that you will see information that you have not seen before in this session. In tomorrow's session, we'll answer how again, but from a more advanced concept standpoint. We'll talk about important monitoring parameters for advanced evaluations. We'll talk about variation in condenser design and how it affects their performance. And we'll talk about when there are opportunities to address condenser design issues. We call those engineering projects, we call those retrofits. And so when are the opportunities to address an underperforming condenser when it's designed it can be better. And then we'll talk about how much. We'll answer the question how much. What are the benefits and the costs for going forward with some of these condenser retrofit projects. Okay, so with that, let's answer the question why. Why do we care about the condenser? Well, on this slide is a diagram of a typical steam power plant. You can see the three major components. You can see the boiler here. You can see the HP, IP, and LP turbines here. And you can see the condenser down here. Now, I want to share with you a story that highlights why we see our work as being valuable to the industry. I attended an EPRI heat rate improvement conference several years ago, and it's a great conference. If you haven't been, the heat rate improvement conference is usually very well attended, lots of excellent papers, and EPRI, as always, they make very good arrangements for these conferences. But this conference, this heat rate conference, is separated into three different sessions: a boiler for boilers, turbines, and heat exchangers. And at this conference, much of the first day was spent talking about the boiler combustion and performance. You know, it's a large piece of equipment. The boiler relies on many supporting systems. There's a lot of neat engineering problems to tackle when they involve operating and maintaining a 15-story fireball. I can understand why an engineer would get some satisfaction, you know, developing skill in this area. Some of the second day at this conference was dedicated towards turbines, turbine dense pack upgrades, turbine maintenance, the latest in turbine technology. And again, you know, the turbine is a very expensive piece of equipment with very precisely engineered and manufactured parts. And again, there's some very interesting engineering problems that ensuring reliable and efficient operation of this, you know, very expensive piece of equipment. And again, I can understand why an engineer would get some satisfaction developing skill in this area. And so at the end of the second day at this conference, the end of the turbine session, they had a roundtable discussion at this heat rate improvement conference. And during this roundtable, participants, they were invited to approach the microphone and ask questions to these panelists. And a young lady engineer came up to the mic and she asked a question. She said, "I'm a new engineer. I'm trying to make some contribution to improve heat rate at my plant, and I don't know where to begin. I don't know where to start. What advice can you give me?" And it was Joe Milton, who at the time was a senior thermal performance engineer with RRI. He answered with 3 words, but they were the same word, repeated 3 times. He said, "Condenser, condenser, condenser." And I'll never forget that. Now, the condenser is by no means a cool piece of equipment. If you were showing someone a power plant, you would show them the turbines, the boiler, probably pass right by the condenser without even mentioning it. You know, on the steam side, it's rusty, difficult to navigate, confined space. On the water side, it's one of the most foul environments in the power plant. This gentleman, his name is Neil. He told me once he entered a water box. He was doing an inspection before we were installing some equipment, and he entered a water box, and he showed me the pictures. There's this red-colored mud all over the walls of the water box and on the floor. You know, he stepped into like inch thick of this mud, and he told me when he was in there, he said that the mud was moving around, and you know, this is clearly one of the most foul environments in the power plant, but it may not be the most desirable place to spend your time, but it contributes to power generation efficiency in a big way. And so let's take a look at how the condenser affects efficiency of the Rankine steam cycle. This chart, you're probably familiar with it. It's the Muller diagram. On here is a Rankine steam cycle for a two-cycle system, so just an HP and an LP turbine. And this chart on the Muller diagram shows the enthalpy, or energy per pound in the water throughout the steam cycle, versus the entropy, or the energy that does not contribute to work. And so it's essential to understand this chart because it's really the basis for developing an understanding and developing algorithms to determine the efficiency of power generation. And it's a great tool to describe why we care about the condenser. And so if we walk through this Muller diagram, we start at point A here, which is down here in the lower left-hand corner. This is the point at which the water in the steam cycle is at its lowest energy point. This is where the water is at the bottom of the condenser. It's at maybe 90 degrees Fahrenheit. And the enthalpy is around 70 BTUs per pound. The water exits the condenser, goes through the condensate pumps, through the low pressure heaters, the deaerator heaters, through the boiler feed pump, all the way while heating up, goes through the high pressure feed water heaters, the boiler, turning the water into steam. All this time the enthalpy is increasing in the steam. We're adding energy to the water. And then it gets up to point H where it goes through the turbine throttle, exits the turbine throttle, and the steam starts to expand and lose temperature and drop in pressure as we push it through the HP turbine. And we convert some of this thermal energy that's stored in the water, we convert that to work in the turbine. Then that steam exits the HP turbine, goes through a reheat cycle. We add energy back into the steam, and then that steam is driven down through the LP turbine. So again, the steam expands, it drops in temperature and pressure. We extract energy from that steam and create work. And so then the steam exits the turbine at a condition determined by the condenser. The condenser determines the pressure and temperature of the steam leaving the turbine. And so you can see here on this diagram that these points M, L, O, and some others, they're determined by the different condenser pressures. And so the lower the cooling water temperature we give to the condenser, the cleaner that we make the tubes. If we keep air and leakage low, we can reduce the condenser pressure, and we can reduce the enthalpy of the steam leaving the turbine. And what that does is it increases the amount of available energy to the turbine, the LP turbine, to create work. So lowering the condenser pressure directly correlates to generating more megawatts. And then as we complete the cycle, the steam goes through an instantaneous phase change on the condenser tubes, and we dump all that heat that we added in the boiler and all the low pressure feed water heaters, we dump it out to the environment, to the cooling towers, to the air, or into a river or cooling water pond or wherever the water source is. So there's a tremendous amount of energy that's discharged. It's a waste product. So now that we know, how the condenser contributes to increasing efficiency, let's take a look at some rules of thumb for quantifying that. So in EPRI's Thermal Performance Engineer's Handbook, you can see that here, down here at the bottom. There's the technical report number. There's a table 2.1, that lists, that allows you to calculate the difference between, gives you the effect on heat rate of different parameters in the plant. And so what I've highlighted here is that every 1/10 of an inch decrease in condenser pressure correlates to about a 0.1 to 0.4% decrease in heat rate, or if you're looking at generating more megawatts instead of heat rate, it's a 1 to 4 megawatt gain for every 1,000 megawatts you're generating. Now the condenser has a rather large range of effect on heat rate impact, and we'll discuss later why that is, but this is a great rule of thumb to give you an idea of how much condenser pressure affects heat rate. Now this is a useful number to know, but typically what might be more useful is how the condenser pressure typically ranks its impact on the power generation efficiency and compared to all of the hundreds of systems in the power plant. And so to take a look at that, we turn to another EPRI document. This is the heat rate improvement manual down here. And here's the technical report number here. And so in this guideline, they go on to rank controllable losses in the power industry. The list is ordered by the far right column, which is the impact to the unit heat rate for typical deviations from the expected operation. And you can see what look at what tops the list. I've got it highlighted. It's condenser pressure. And its typical impact is equal to a heat rate deviation that is almost double the impact of the next highest typical controllable loss. So this is why Joe Milton made his comment. This is why we view our work as valuable. This is why he recommended to that young engineer to invest her time and resources into the condenser. And hopefully today and tomorrow you'll learn something new, or we'll be able to evaluate the condenser from a different perspective and make some changes on these orders in your own plant. Okay, so that concludes the section on why do we care about the condenser. So let's take a look at what we should be monitoring. So we'll take a look at some basic condenser terminology, and we'll talk about I'll present some of the important monitoring parameters for basic evaluations. So there's only one slide on terminology. I really put this up here because sometimes when I speak to people, I use a terminology that they don't use in their own plant. Like, for example, sometimes I will call this non-condensable a vent, even though I know it's not a vent. When I say vent, most people think about this water box connection here that's used to vent out air or pump air out of a water box for priming the water box. So this water box vent here, it's for ensuring that the water boxes are full of water. Again, the water boxes can be under pressure or they can be under vacuum, in which case you would need a vent if it's under pressure, or you would need a whole vacuum system with vacuum pumps to prime these boxes if they were under vacuum by design. So then the non-condensable, or in the nuclear world they use the term non-condensables because there's more than just air in the steam space, particularly in BWR plants. That you have hydrogen and oxygen from the nuclear from the reactor gases, and they enter the condenser. So in the nuclear realm, they call them non-condensables. For all the fossils and PWRs, you would refer to it as air. But this is where the air is removed from the steam side of the condenser. Now, this is a Westinghouse condenser that I've shown here on the right-hand side. It's a little bit different from many other condensers. Most condensers will have a shroud, and I'm drawing a shroud here down in the bundle, and it'll have a pipe that comes up through here. And the air offtake will actually come out of the transition region of the condenser out through here and then go off to the vacuum equipment. But in this Westinghouse design, it actually comes right out the tube sheet in through this flange here. It's completely sealed in the water box through this pipe and comes out another flange here and goes off to the venting equipment. But that's the non-condensable or air offtake of a condenser. Then we have obviously the water boxes that contain the cooling water, or some people refer to it as circulating water. Then there's the air removal section, and it's also referred to as the air cooling zone. You may see that it's called the air cooling zone on your condenser spec sheets. And again, the air removal section and air cooling zone typically is defined by some type of shroud in the condenser. The Westinghouse doesn't really have that. Then there's the tube bundle. We define a tube bundle as a set of tubes with one air removal section. That's what a tube bundle is. And then the condenser shell. The shell has really three main components. It's this shell here. There's the transition region up here. There's the neck that connects to the turbine and contains the dog bone joint there. And then lastly, there's steam duty. So some people refer to it as steam flow, some as steam duty. Steam flow typically refers to a mass per time unit. Steam duty refers to an energy per time unit, at least in our terminology. So that's all I'm going to say about terminology. I'd like to move on to some other probably more important things here, is condenser configuration. Now, thing about condensers, they can be configured in all different kinds of ways. We'll talk about the outer configuration, but right now I want to focus on the internal configuration. The internal configuration, you can have feed water heaters up here and whatnot, but what I want to focus in on is the tube bundle pattern. So I've animated this slide to show you what a tube bundle pattern can look like. And there are so many different designs of tube bundle patterns. They're very wide varying. And one of the things we have access to here at Intech, we do a lot of condenser redesign and engineering and research projects on condensers. We have access to a whole library of different condenser designs. And as you look over them, you get a sense for the designer's attempt to improve condensers over time. You see where they've tried to make things better by designing the bundle in a different way. And you see progressions over time. And when I first looked at these and all these different condenser designs, I compared it to the early days of flight when man was trying to invent all of these crazy machines to try and fly. And I'm going to show you a few slides here, upcoming slides, maybe 8 or 10 slides here, where they're meant to be a little bit silly, but they show a condenser bundle over on the right, and they'll show a early day flying machine over on the left. And as I scroll through some of these, I want you to take a look at the condenser design over on the left, on the right here. And what do you see in the design that would make this bundle pattern better or worse from a performance standpoint, or even from a maintenance standpoint? So I called this one the umbrella design. It's got this upper half here and a lower half. Kind of reminded me of this flying machine. So take a look at this bundle. Is this bundle any better or worse than the last one? Do you see any features in it that would make it better from a performance standpoint or a maintenance standpoint? And we'll move on to another one. This is a prevalent design in the industry. It's the Westinghouse design. We'll talk about this one quite a bit. Here's another design with all of these lanes in it, reminding me of this multi-winged plane. So are there any features in this that make it better or worse than the previous ones that you saw? Here's one. One of these, I've seen several of these, one in particular in a nuclear plant in the United States. This one has an air removal section down here. Here's another design. And yet another one, sort of similar to the last one, but with this big opening between the two upper half and lower half of this bundle. Here's another one. I think this is a Foster Wheeler. And so, as you look at all those different designs, some of them there are some similarities, but there's a lot of differences. And so there's a wide variety of tube bundle designs. And the performance of these bundles definitely changes with the design. And so that's something that we will tackle not so much today, but tomorrow. In tomorrow's session, I'll be able to show you with very detailed measurements that we've made on several different condensers where the low performing areas are in these bundles. And so you'll get to see how they react for different operating conditions, and we'll talk about ways to improve designs that are not quite optimal. Now there's another aspect to condenser configuration. It's kind of the envelope, what I call the envelope of the condenser. The condenser can have one pass of cooling water straight through it, in and out. It can have a two-pass cooling water flow path, where the water comes in, turns around, and goes back through warmer. You can also have multiple shells on a condenser. So these shells could have different pressure compartments. So here the water comes in cold, it warms up as it goes through the low pressure, enters the higher pressure shell. Now there's low pressure turbines tied to each of these, but they operate at a higher pressure and a lower pressure. You can also have multiple shells up to 3 or more, or the shells could be a single shell with multiple zones or pressure zones in it, like this. And each one of these needs to be evaluated a little bit differently. Let's take this case down here, for example. In this particular condenser, you don't have a way to make a measured outlet temperature or inlet temperature to the HP shell, an outlet temperature to the LP or an inlet temperature to the HP shell. And so there's different techniques to use when evaluating the performance of a condenser with a different type of design. So that completes a review of the terms that I wanted to use and some of the configurations. But now I want to talk about describe the condenser components from the heat transfer standpoint, heat transfer terminology. And I frequently hear system owners talking about using temperature rise across the condenser to troubleshoot fouling without truly understanding what's happening. So so having a strong understanding of heat transfer fundamentals will prevent you from making mistakes like those. So shown in the upper left-hand corner is a cross-section of a condenser showing the steam entering the condenser here, and transferring energy to the cooling water, giving up its latent heat of vaporization. So here's the cooling water warming up as it goes through the condenser. Now this warmer water, as we saw from the malaria diagram, contains a huge amount of energy that was given to it in the boiler, but was not used to create work. So let's take a closer look at the thermal circuit to introduce the concept of a heat transfer coefficient. Now the heat transferred from, call this point A to point B over here, through thermally resistive layers, these R's here, is directly proportional to the temperature difference between point A and point B by 1 over R. So we've given that equation here, Q equals 1 over R equivalent times delta T, the temperature difference from point A to point B. And so this R equivalent is just the summation of these impedances. Now I'm going to show you an illustration of the thermal impedances that exist on a tube. And so here they are. So this is a tube. This gray section here is the tube. But first, the first impedance that the steam encounters when trying to transfer its energy to the cooling water is a non-condensable or air layer. Now, it's important to understand that this non-condensable layer can actually dominate all of the thermal impedances in this system. It could be 0, or it could actually dominate the entire heat transfer process. But once it makes it through that layer, there is a condensate film. This condensate film, you can use Nusselt equations, Nusselt coefficients and analysis to determine the heat transfer through that layer. Then there's the tube material, and it has a certain thermal conductivity, so you can calculate that R sub T. Then there's waterside fouling. The fouling could be a calcium deposit, could be manganese deposit, could be mud. And so there's a thermal impedance to heat transfer through that layer. And then you have another impedance determined by Nusselt type equations, and that's the convective heat transfer through the water from the inner layer of the tube or fouling to the cold cooling water. And so that's the thermal impedances that are seen in this heat transfer process from steam to cooling water through the tube and all of the thermal impedance layers between them. So now I want to take a look at this diagram in the lower left. This describes some of the temperature nomenclature that I'll use in some equations next. We've got T sub circ water inlet and T sub circ water outlet. We have the Q here, the duty that's being heat that's being transferred to the cooling water, and we have the steam temperature, the temperature of the steam that's approaching the condenser tubes. Now, in the previous slide, we had Q equal to 1 over R delta T, and in this scenario, it's roughly the same thing. Here's Q here, and we have U, the heat transfer coefficient. U times A is the same thing as 1 over R. And now instead of delta T between points A and points B, we have used Fourier analysis to come up with delta T LM, the logarithmic mean temperature, which is the temperature difference between the steam temperature and the logarithmic mean of the cooling water inlet to outlet temperature. And so this is essentially the same equation. There's the equation for the logarithmic mean. Another equation that's important is the duty that's transferred to the cooling water, Q, is equal to m dot C sub P delta T. So that's another important equation here. U is just the inverse sum of all these impedances that we talked about up in the upper right-hand corner. And so the reason why I introduced these equations is I want to, from a fundamental standpoint, illustrate how condenser pressure increases in the condenser. So if we keep the duty constant, you keep the load that's being given to the condenser constant, you keep the surface area, the condensing surface area constant, so those are equal. But any one of these resistances increases, whether it's due to air in leakage, fouling, or anything like that. If U decreases, then the delta TLM has to increase. Now, because of this equation down here, if Q stays the same, your inlet and outlet temperature don't change. So if you foul, the inlet and outlet temperature, bulk temperatures, do not change. So the only way that delta TLM can increase is by increasing the steam temperature, or increasing the temperature difference between the steam and your cooling media. And so that is why when you foul, the condenser pressure increases. You require a greater temperature difference to get the same amount of heat transfer through a more resistive, a lower heat transfer material. Okay, so that concludes the what. So now let's get into the, I guess, the more important stuff, the how. How do we calculate target values? Then we'll move on to some of these other things. So far I've presented general condenser component terminology, heat transfer terminology, all of that stuff. Now let's take a look at the instruments that most of you have to monitor the condenser performance. And that's what we'll talk about in the basic section today is the instruments that you most likely have at your disposal. This graphic is used in the next several slides to guide us through all of the instruments to monitor the condenser inputs and outputs. That's the way I like to look at different operating systems, is if you can list all of the inlets, list all of the outputs, you can kind of, and know the process in between, you can connect everything together. So first, inlet to the process, condensing process, is the inlet temperature, and we'll talk about the outlet temperature here as well. There's some guidelines on how to make this measurement. RTDs are the ASME Performance Test Codes 12.2 is the standard for making condenser performance measurements. They provide excellent guidelines on how to make these measurements, how to do them the right way, and how not to make errors. So RTDs are recommended over thermocouples. Those instruments that you install should have a plus minus 0.1 degree Fahrenheit uncertainty. And it's important to understand from an instrumentation standpoint, if you just purchase a Class A RTD, that RTD comes with a almost 0.25 degree Fahrenheit uncertainty with it, and a nonlinearity of 0.15 degrees Fahrenheit over a usable temperature range of 32 to 122. So just buying an RTD and you hook it up to a transmitter, it needs to be calibrated to get these types of uncertainties. Performance Test Codes 12.2 also gives some recommendations on locations. Location is very, very important for making outlet temperature measurements. Outlet temperature measurement can be made up to 1,000 diameters downstream of the condenser. And what that recommendation is you want to make it less than 1,000 diameters downstream of the condenser to avoid significant losses, thermal losses to the environment. That's why they have that recommendation there. And then they also recommend an array of no less than 5 measurements in a location that is stratified less than 0.2 degrees Fahrenheit of the average. And they recommend a traverse, a linear traverse for this measurement, but we'll talk about how to make this measurement the right way in a few more slides, and we'll show some real test data from the field. But why do we want to make these measurements? Well, the inlet temperature error can cause of 1 degree can cause up to a tenth of an inch error in your target calculations for pressure, and also 1% error in delta T will correspond to a 1% error in your duty calculation. So it's important to get this measurement right to do a good performance analysis. Circulating water total flow. These are the guidelines. Again, we'll talk about some good ways to make this measurement. I think in tomorrow's presentation. But ASME Performance Test Codes 12.2, they recommend velocity traverse. That's a good one if you have access to a straight run of piping, like on a cooling tower, to do a velocity traverse. They also recommend tracer dilution. You got to be careful here because there's you have to get the chemistry right to make this measurement come out right. Sometimes the chemicals used for the tracer chemical can actually react with some chemicals in the cooling water, so you have to be careful about that. But it's a good method to measure cooling water flow. Ultrasonics are a way potentially to measure it continuously. But some of them don't meet the 3% accuracy requirement of a performance test code. Differential producers, this is a really good way to do it. This is a way that we recommend. It's economical. If you do it the right way, you can have a continuous measurement of cooling water flow rate for a very long time for not much cost. And so we'll talk about how to do this. The last way to do it is to do an energy balance, and so you don't actually measure the cooling water flow. You have through your turbine thermal kit or some other method, you have a calculated duty that's going to the condenser, and using this equation here, you would calculate your cooling water flow rate. There's another method. Single tube meters can be used in clean systems. So these are meters that get attached to individual tubes. So you would install an array of these on the condenser to get a flow rate. They have the potential to foul over time, but there's other uses for these single tube meters, and so it's a method for getting a flow rate that might be used to calibrate a differential producer. And we've used this several times. So why measure total flow? Well, it's really a critical measurement to make. You need it to calculate duty if you don't have access to duty. There's 5% error in total flow can cause 5% error in calculation of duty, and other parameters derived from that. So another reason to measure total flow is it can assist with compliance with some environmental regulations. Condenser pressure. This is one of the most critical ones. It is the most critical, actually. Condenser pressure is very important, and PTC 12.2 has these different recommendations here. They recommend absolute transducers, a maximum uncertainty of 2/100ths of an inch of mercury. They recommend 2 or 3 locations depending on your shell layout, 1 to 3 feet, no more than 3 feet above the top of the tubes. That's an important specification there. They also recommend static pressure taps, basket tips, or guide plates. Now, most commonly, we find this measurement to be an error via various different reasons. Either it's in the wrong location, there's water traps, there's other issues. And so in a few slides, we'll talk about some of the errors that we've seen and what our recommendations are to make this measurement the right way. So why measure condenser pressure? It is the most critical measurement. A 1/10 of an inch error can cause 0.1 to 0.4% error in your heat rate change calculations, or 2 to 10% error in your performance factor or your cleanliness factor calculations. Those ranges are highly dependent on starting cleanliness. Okay, so that's what should be measured for a basic performance evaluation. So now let's talk about calculating target values. Very important to know where you are and trend it over time so you can monitor performance and take action when things start to go south. So let's talk about, let me present some things on calculating target values. Now this is a diagram that I like to use to identify what's needed, what things you need to get to a HEI cleanliness factor or an ASME performance factor. And so if we take a look at, by the way, this chart is divided up into, the green stuff is the items identified in green. There's basic instrumentation for basic evaluation. So all of you should be able to do this with the instrumentation that you have in place. This type of analysis, identifying fouling, air storage, things like that, you probably need a more advanced instrumentation, but we'll talk about that tomorrow. So let's take a look at the basic evaluation side of things. We need this information here. We need duty, cooling source information, design information, and condenser pressure to calculate our heat transfer coefficient and our cleanliness factor. Now there's 2 different methods to monitor performance. The HEI method is almost used exclusively, and this is the one that I would recommend to use for monitoring performance of the condenser. HEI recently released its 11th edition, I think in 2012, I think it was. They released the 11th edition. There have been very slight changes made over the years. I'll show you one of the most important ones in recent past here in a couple of slides. But just a little background on this method. The general equation was developed by Arup in 1910 before some important new salt analysis had been finished. It is a heuristic method. So it's based on operating data from condensers of various designs. So it's basically an equation that fit condensers made in that era, and it's been updated throughout the years. It is updated by condenser manufacturers, and it is the design standard in the industry around the world, actually, for main condensers. The other method is the ASME resistance summation method. Now this is important too. It should not be ignored, but really the application for this method is when you're conducting performance test code. So a newly installed condenser running a PTC 12.2 test. You would need to know this method to correct your measured data to the design reference. And I'm not going to go into this method. It's pretty detailed in the performance test codes. It's about an 8-page summary calculation, so it's quite complex, but it's used. It is the standard for conducting this test, and it's based on first principles. It's not an equation that condenser manufacturers have made. It's an equation based on first principles. It matches well to data obtained on single tubes in laboratories, but it does not really accurately identify what you should expect from a condenser used in industry. It does calculate heat transfer coefficients higher than HEI by about 25%. But it is a good method to do this correction for the performance test codes. So let's talk about the HEI method. Everything that you need to do your analysis using the HEI method is included in the next couple of slides. This is the basic equation here. The heat transfer coefficient according to HEI is a product of all of these different factors here. And we're going to talk about each one of these in the next couple slides. One last comment to mention about HEI is that if you read this paragraph here, and I'll call out some things here. Let me see if I can find it. Let's just read it. The design of a steam service condenser must consider the effects of non-condensable gases which are present in the condenser, pressure drop of the steam as it flows in and around through the tube bundle, and tube inundation as it condensate falls through the bundle. And here's the kicker right here. Due to these effects, the heat transfer coefficient of a typical commercial operating condenser is less than attainable in laboratory tests. Okay? And so this method that they have come up with allows for these things. Okay? It says right here, this method includes an allotment for the steam side effects described over here. Okay? So this factor right here is called the cleanliness factor, and that is a cleanliness margin that you as a purchaser and the manufacturer agree upon. But the translation of all of this is that your condenser should reach, if you were measuring this cleanliness factor rather than using it for a design, if you were measuring it, it should reach 100% after cleaning. If it doesn't, then something is degrading performance. Now, I'm not saying that you should get 100% after every cleaning. I'm just saying that something is degrading the performance, and it's important to know what that is and to figure out if there's something you can do about it. So let's talk about each one of these factors in the HEI heat transfer coefficient. The first one, this one here, deals with the convective heat transfer in the cooling water. And so the faster the water goes, the better that convection is, and the higher the heat transfer coefficient you get. So this is the U based on the velocity. Now this U gets modified via inlet temperature inlet temperature and tube material, but this gives you a starting U value as a function of velocity and the tube ID or tube OD. And so you would find your design flow rate or your operating flow rate and grab this U to start off to identify this parameter here. The next parameter is this F sub W, and this is a factor that accounts for all of the water properties that change with water temperature. So down here, this should say T1 down here. It's been cut off. Your inlet temperature. So the viscosity, the thermal conductivity of the water, the heat capacity of water that changes versus inlet temperature is accounted for in this factor here. And something to note about this is that this has changed quite a bit from the 8th edition. This is the line that was provided in the 8th edition, but just wanted to show you that this standard does change over time. It gets updated. So then the last factor is the tube material factor, F sub m, and that's just a lookup table here. All of these factors are based on an 18, well, they used to be based on an 18 gauge. This used to be a 1, but now it's a 0.998. But here are the tube material factors for this factor here. So you can take a look at your tube gauge up at the top here, your tube material, and grab this number and plug it into the equation down below. And so that's all the inputs you need for the HEI method. The last bit that you need is these basic formula, these key equations here. And so on this slide you can see a sample calculation and use this to come up with your own cleanliness factors or even evaluate. I would highly recommend evaluating, if you're using cleanliness factor now, evaluating your formulas, because we found in many cases errors in these formulas in operating plants that result in a cleanliness factor that's just not useful. But these are the equations you need. This one here, which is QU A delta TLM. This one here, which is the energy balanced equation, Q equals m dot C sub P delta T, and then this one down here, which is the HEI formula that we just talked about. Okay, so cleanliness factor is what we recommend to be the best value to trend to monitor performance. You need the design information required for all analysis. You would need this. You need design information, tube count, tube material, tube gauge, tube length, all of that here. And then you need any three of these 4 items to calculate cleanliness. You need 3 of those 4, and then use the formulas on the previous slide to calculate your cleanliness factor. And you need condenser pressure, of course. So any of those 3, 4, plus design information, plus condenser pressure, and you can calculate cleanliness factor. Now, a lot of people can refer to TTD. They use TTD, but it is not really a reliable benchmark for performance. And it's for 2 reasons. The outlet temperature is often unreliable, and we'll talk about that. And also a lookup table. You have to use a lookup table to compare the measured value to the achievable value. And these TTD values change with inlet temperature, duty, and flow rate. And so if these things are changing on you, then you need a lookup table to figure out if the TTD has deviated from the achievable value or not. So the cleanliness factor is really just a much better way to troubleshoot your measurements as well as monitor performance over time. And so once you get all those formulas down, and you can make a plot like this. This is what we call a bogey plot. And so you would filter your data for a given steam load. You would plot your measured condenser pressure versus your cooling water inlet temperature, and you would get a cluster of data like this. And then you can use those formulas at different cleanliness factors, fixed cleanliness factors, and calculate where the pressure should be for the design point, where it should be for 70% cleanliness, where it should be for 90% cleanliness, and you can compare where you are to where you should be. Like you can calculate the difference would be your achievable condenser pressure. And that achievable condenser pressure is important for valuing condenser performance, and that's what I want to talk about next. Now you can use this rule of thumb. We talked about this Thermal Performance Engineer's Handbook rule of thumb. You can use this to estimate, but there's a better way to do it. And since we showed you on 2 slides ago or 3 slides ago how to calculate your target pressure, and we talked about how you can compare it to your measured pressure, you can grab this curve, which should come with your turbine thermal kit. This is a turbine heat rate correction curve. Now the curve may be a little bit different. It may be power generation correction curve, or it'll be a change in heat rate correction curve. But essentially what you'll have is on the x-axis the condenser pressure, and on the y-axis either a percent change or megawatt change. And then you'll have these different curves here. And each curve corresponds to a different main steam flow, or main steam flow through the turbine. And so how you use this graph is you choose the main steam flow. You could create a surface to fit all of this data, which is what we do for more complex analysis, or you can pick a curve or draw a curve in for a fixed duty and do analysis on filtered data for fixed duty. But what you do is you pick your curve here, you plot on here your measured pressure at this star here. So this measured pressure, this condensers that we're evaluating, is operating at 2.5 inches. I know this is very difficult to see, but this says 2.5 right there. And we calculated our target pressure using the methods that we just talked about on the previous slides. Our target pressure is 2.0. Okay. And so now we do this correlation here. We can get the rise for this run here, and we come up with looks like what is this? Looks like 2.4%. 2.4% for this half-inch change. Yeah, that's a 0, that's a 2, that's a 4. Yeah, that's right. So 2.4% change for this half-inch pressure reduction. And that's how you can value the impact of reducing your condenser pressure by, again, reducing inlet temperature, reducing air and leakage, cleaning the tubes, whatever it may be. Okay, now there's different ways. There's also different ways. This is a way for determining heat rate, and if you have a power generation, calculating extra generated megawatts. If you're operating in a turbine follow mode, this method will give you, you can calculate how much how much savings there is in less fuel usage. If you're in a boiler follow operation, then you're not saving fuel, you're actually putting more megawatts on the grid. So this is actually more beneficial if you cost doing some change to the condenser using a boiler follow operation for your unit. Then there's recovering derates from excess condenser pressure. So typically on hot days in the summertime, if you can estimate your recovered megawatts by keeping the condenser pressure below the turbine limit, that's another way to value condenser performance. Variable speed cooling water pumps, for the very few plants out there that have these, if you can cut back on your cooling water flow usage, you can save station power and deliver more megawatts to the grid. And typically you would only do this in the winter times when reducing condenser pressure does not favor the efficiency of power generation. And then one last note here about condenser performance is condensate subcooling. Some units operate with a lot of subcooling, and 5 degrees Fahrenheit of subcooling can be a 0.05% heat rate reduction, or actually increase on your heat rate. And there's the reference for this as well. So now I want to talk about some common performance analysis problems. And so this is where we take all of this theory and recommendations for instrumentation and take a look at some practical limitations, practical issues that you may encounter at your facility. So here's a graph. Here's some data from an operating plant. What we have here on the y-axis is condenser cleanliness plotted over time here. And this is the performance values that the engineer I was working with was looking at. You can also see on this graph, that's, by the way, that's the yellow line here. This is cleanliness here. We also have on this plot is generated gross megawatts here. That's this black line here, black data. Now you can see here this engineer was a bit perplexed. He saw that the cleanliness or the performance of the unit increased when they went up on high load and decreased when they went on low load. And you know, we see this a lot. There's reasons that this can happen in a plant. One of them is at lower loads, the unit operates at a lower pressure, your vacuum equipment operates at a lower pressure, and you can't remove as much air from the condenser. So well, I guess we'll get into that later, but this happens in some cases. But the person that I was working with at this plant, he had already installed test grade instrumentation. So he had test grade temperatures, pressures, even flow rate in his plant. And I told him, I said, well, before I give my verdict on what's causing this, let me compare the test grade measurements to the original equipment that's being used to calculate this AspenTech. This AspenTech is their historian that's being used to calculate this performance parameter. So they're using the station equipment, you know, installed back in the 1970s or 80s to get this number here. And I said, well, let's take a look at the test grade measurements. And so when I did that, we took the test grade measurements, and when I recalculated condenser performance, this is what I got. So this is the same time period. So there's the cleanliness of the station equipment, using station equipment measurements. Now here's the cleanliness using test grade measurements. Okay, and the cleanliness is pretty much stationary throughout this time period. Now it changes on these transitions. They had some unique issues with data averaging. You can see all these straight lines in data averaging, and also some lag in when the measurements were being reported to the historian, which caused these spikes at every transition, load transition. But you can see here very clearly that at low load they're operating at 80%, and at high load they're operating at 80%. So what was causing this? And I want to talk about these because you may use this information to troubleshoot some issues in your own plant. First one was condenser pressure. And so here on this plot, let's see if I can highlight it. All of these values are the station original equipment. And these values down here are the test grade instruments. Okay. So what we can see is right away that you've got this outlier here, and you've got some spread in this data here. And so what it turned out that their alpha 1 pressure sensor was being affected by something in the condenser. I suspect it was, by the way, all of these measurements were not made 3 feet above the bundle. They were made much higher in the condenser, which is very common. So there's a location issue there. But this one here, I suspect, was located near a drain or some type of drain that was operated intermittently, causing its value to deviate like this. Now with the test grade instruments, we have, let's see, those are right here in this tight, there's the test grade instruments, 2 of them there, and they are right on top of the saturation pressure calculated with their hot well temperature, right there. And so test grade measurements can give you a much better measurement of what's actually going on in the condenser. So the recommendation here was to abandon these pressure measurements that are really not in a location adequate for monitoring condenser performance, and to use the test grade measurements or some other measurements that they had, like at the hot well temperature, to use to determine the conditions of the steam for performance monitoring. So that was one issue. The other issue is that their inlet temperatures, the cooling water inlet and outlet temperatures, were skewed. So at this particular plant, we had installed 55 test grade temperature sensors, and we'll talk about where those were installed probably tomorrow. But there's 55 of these installed in this plant, and you can see here that their station original equipment was far from accurate. So we had both an A inlet and a B outlet temperature that was not that was reporting a value almost a degree off of its off of the true value, which is a pretty big error. Oh yeah, that's thanks, Colin. One thing to point out is that this data was obtained during no load conditions. So the cooling water is flowing and there's no duty to the condenser. That's the time to do this type of analysis. So there's water flowing from inlet to outlet, no duty to the condenser, no temperature rise, and that's where you can compare your inlet and outlet temperatures. Thanks, Colin, for that important clarification. Okay, so with those, there was also one more error that I didn't talk about here. They had an error in their calculation, their formula. They were using the wrong size tube, and I think there was a velocity calculation that was causing a few % error. But the bulk of the error was the pressure sensor and the temperature sensor error. So once those were corrected, we got them to a much more usable, much more consistent metric for monitoring performance. Okay, so here's another case study, another unit. Again, here's the cleanliness factor, and shown in red this time, and the gross megawatts here for this unit. And so you can see here, you see these changes in cleanliness for almost no change in apparent operating condition. And so at this plant, they had also installed some test grade instrumentation to clean this up, and as well as for some other reasons. But here is what the cleanliness calculated using test grade instrumentation. And so what's shown here is a yellow line, which is IP, what we call the IPFD, FDD, and IPDO. So if you recall a few slides ago, I said to calculate the cleanliness factor, you needed to know pressure, design information, and then 3 of 4 other parameters. And so it's useful sometimes to go ahead and calculate as many of those as you can using different 3 of those 4 parameters and comparing them. And in doing that, you can find the best one to use for trending, as well as find other errors in measurements. And so the IPFDD is the inlet temperature, the condenser pressure, a design flow rate, not a measured flow rate, but a design flow rate, and the duty that was coming from their turbine thermal kit. Now, IPDO is inlet temperature, condenser pressure, duty coming from their data historian, and the outlet temperature of this condenser. And I believe this condenser, we installed some test grade outlet temperature sensors. And so now you've got a much more trendable, a reliable cleanliness value if something were to go wrong and the cleanliness were to start dropping off you would know that it was real and could take action. So here's what we found in this particular case. So here is the station original equipment measurements, shell pressures, hot wall temperatures, hood temperatures, and down here the solid colors are the test grade instruments, and if we blow up, I think we have a, yeah, there we go. So these numbers in the legend over here correspond to the cursor values at each one of these locations. And so let's see what we can see here. You can see here that shell A and shell B, they have a cross connect between them, so they should be operating in the same pressure, but the station equipment shows them operating at a pressure that's 0.3 different from each other. You can also see that the exhaust hood temps are roughly the same, but they're actually lower than one of the shell pressures. But now if we take a look at the test grade sensors, and we can see that both shells are operating at about 2.8, 2.75 to 2.8 inches of mercury. And what we typically recommend is, if you're going to go through the effort of installing test grade instruments, don't just measure pressure, because pressure is sometimes difficult to measure, but also measure temperature, measure the steam temperature. And so the equipment that we recommend has both pressure and temperature sensors on it, so you can make both two independent measurements, and then you have a very high confidence that you're making a good measure of the steam properties. And so the saturation pressure based on the temperature measurement of this test grade instrumentation is almost an exact agreement with these measured pressures. And so this error in pressure was causing much of the error in the cleanliness factor here. Okay, so let's talk about a little bit more specifics. Measurement accuracy requirements for pressure can only be met by high-end absolute pressure instruments and properly located tap locations. That is probably one of the most common problems, is the location not being appropriate for pressure measurement. The other thing that we see a lot is just that some of the station original equipment just is really can't meet this spec. And so here's an example of a pressure sensor in an operating nuclear power plant. It has an upper range limit drift per year of 0.1%, which is already, the uncertainty already is 0.04, which is greater than the PTC recommendations. But then you add on top of that this upper range limit per year drift and temperature effect drift, and you're way off the mark for having a reliable pressure measurement for performance monitoring. We often see differential pressures transmitters used in operating stations as well, so just going up and looking up the model number and checking that out can be a valuable exercise. Just as a general, to reiterate that specification that the measurement needs to be made 1 to 3 feet above the bundle, here's just a pictorial example. Now, one thing I also wanted to add is, this is, in some cases, we do see temperature and pressure measurements made along the sidewall of the condenser, even just above the hot well, and those generally turn out to be very good measurements for performance monitoring. But since they are not recommended by the PTC spec, they're not usually recommended, but there is evidence of them being useful for performance monitoring. Pressure tap types. PTC 12.2 recommends a basket tip or parallel plate tap. Properly positioned static taps are also acceptable, and they can reduce the installation cost if you do the due diligence to approve a certain location for a static tap. Make sure it's not near any high velocity drains or dumps, and locate them properly. we recommend putting them above the water boxes. That's either the outlet or the inlet water boxes. That's generally an area of lower velocities. And also, that our recommendation has been supported by recent EPRI EPRI technical report. They've actually gone through and in this particular plant, actually these pictures came from that plant where they installed basket tips in several locations, parallel plates in several locations, as well as static taps, and found that static taps in the locations I just recommended are actually adequate for performance monitoring. And so you can save quite a bit of installation cost by just putting in a static tap and not using these basket tips or parallel plates. Again, here's an example of circ water temperature and measuring inlet and outlet circ water temperature at no load conditions. So here's another unit that has test grade instrumentation installed here, shown down here, and original station equipment shown here in these colors. And you can see right here, here's all of the test grade instrumentation installed, and you can see how bad inlet and outlet temperatures can be in typical operating units. You're looking at, what is that, 2 to 3 degrees off of the actual value in some cases. Circ water temperature instrumentation requirements. I think we already talked about some of this. RTDs are the best thing to use. There is one thing I do want to talk about is thermal wells located on the water box wall are not acceptable. And so if you see those and you're using those for performance, I can guarantee you're not getting a useful measurement for performance monitoring. The walls of the water box will have water temperatures that are higher than the average in almost every case. So the right way to locate thermal wells for outlet temperature monitoring is to conduct a CFD analysis. And it doesn't take much to do this, but you do need somebody that can representatively provide a representative outlet tube sheet thermal stratification to start the analysis as a boundary condition. And so here is a analysis on a water box that we had done for a Westinghouse condenser. We have a lot of experience with the Westinghouse condenser. And so this is just a model. This is not driven by measurements, but it provided us a method for determining adequate locations for installing thermal wells for temperature measurement. And so what we were able to do is get the right depth, the right location, and get outlet temperatures that were useful for performance monitoring here at this site. Now, cooling water flow instrumentation requirements. So the instrument accuracy requirements can only be met by several methods to conduct a PTC test. It needs to be plus minus 3% of reading. Now, some common problems are total measurement accuracy is often compromised due to lack of a measurement or routine testing. So here are some methods of measurement. We talked about the velocity traverse to the dye dilution. Those are single point measurements. You can't use those for continuous monitoring. Most commonly, this is a method that's used, the heat balance method. There's ultrasonic meters that have also been used in the field, but differential pressure meters are what we recommend, and so I want to take a minute to talk about those. Again, if you're to do this the right way, you do some CFD analysis. You calculate, you do a model of the water box and the piping connected to it. You find regions for taps that will give you the best performance as far as signal range, so usually the highest DP. You also want to avoid areas of vortices, and you want to avoid areas that can cause debris buildup in your taps. And so, using a CFD analysis, you can determine the right locations for these differential pressure taps, and you would calibrate this differential pressure using one of the other methods, using either an ultrasonic or a dye dilution or velocity traverse, or in some cases a heat balance. And so you would come up with a curve like this. You can see here's the pressure drop, at least for I don't think this water box corresponded to this curve, but nonetheless, here's a pressure drop for some DPs that we installed for a customer, and the flow rate per path. That's another nice thing about this differential pressure method, is you can get the flow rate for each path through your condenser, and not just the total flow rate going to 2 or 4 paths in a condenser. Now there's also a right way and a wrong way to do this from a tap standpoint. This is commonly found where you have on the water box pipe, that's what's shown in this diagram, you just have a carbon steel piece of nipple, maybe hooked up to a valve here, maybe with a purging valve here, but then all of this is free to get plugged up over time and corrode over time. And so there's a right way to do this, both in material choice and tap type. We would only recommend using isolated pressure taps with pressure impulse lines on them, and with a purging mechanism so that those can be purged and maintained over time. So that pretty much concludes today. Again, today was a lot of basic condenser information. Hopefully it was useful for those of you that are new condenser system owners. But tomorrow's session, I promise you, will be more advanced. We'll talk about, we'll show you some things that I'm sure none of you have seen before. And so I wanted to give you a preview of what's coming up tomorrow. There's a wide variety of tube bundle designs, as we already talked about, and performance varies with design. And so one design in particular that I'll talk about, and there'll be several of these that I'll show, is the Westinghouse condenser. And so I'll talk about how we go through and evaluate different condenser designs and look for ways to improve them. And so here's one particular project, one of the earlier projects that we had done, a Westinghouse condenser bundle. During a retubing outage, they were going to have some turbine work done. They were going to upgrade their turbine by including a dense pack in their HP turbine. They were going to change tube material from Admiralty brass to stainless steel. And this particular unit, they needed to make this material change, but they were already concerned because in the summertime they were having to derate because of back pressure being too high on the turbine. And so now making this tube material change from Admiralty brass to stainless steel was going to reduce their heat transfer coefficient even further. And so they were very concerned about making the problem worse by doing this tube material change that they had to make. And so we told them that with this condenser design there was a lot of room for improvement. And so we designed a condenser retrofit. We actually changed, without changing these support plates, without changing the tube sheet pattern, we modified this condenser to something that operated much better. And so here's the results. Here's that same curve that I showed before. It's condenser pressure versus cooling water inlet temperature down here. All of this data is filtered for main steam flow of this up here. And so pre-retrofit, the tubes were cleaned, mechanically cleaned. They didn't have very many plug tubes. They were Admiralty tubes. And this is the performance here shown in red, post-cleaning, pre-retrofit. The original manufacturer's design curve is shown here in green. This is with Admiralty tubes. And then post-retrofit, what we did is we installed plates, piping, and we basically totally modified a certain section of the condenser that I'll talk about tomorrow. But we did a very simple modification during the retubing. They retubed with stainless steel tubes, and this is the pressure. These are the pressures they were getting in 2008 and 2009, filtered for the same steam flow at these cooling water inlet temperatures. And so we were able to reduce the condenser pressure below the original Admiralty tube design. Now, another thing I want to point out is that this data was obtained when air and leakage into the condenser was 20 SCFM. This data in the teal was obtained when they were operating at 80 to 100 SCFM of air and leakage. So not only did we reduce the condenser pressure, but the changes that we made this condenser more immune to the effects of air and leakage. And so we'll talk about that tomorrow. And this correlates to about a 1/2 inch to 7/10 of an inch reduction despite the tube material change from Admiralty to stainless steel. Some other retrofit results is a reduction in back pressure for all loads in all seasons. Maintenance effort was reduced due to increase in air and leakage immunity. And condensate chemistry was improved. In this particular condenser design, condensate chemistry was a little bit problematic. And so the changes that we made reduced the dissolved gases in the condensate and reduced the dissolved inorganic carbon in the condensate. And so here's kind of a summary before retrofit. They had Admiralty tubes. The dissolved oxygen was consistently 20 to 35 ppb. They had deep bed full flow polishers. They were pre-coating every 30 days. And they had an air and leak limit when back pressure started to rise of 20 SCFM. After the retrofit, they were using stainless steel tubes. The condensate dissolved oxygen dropped from down to 2 to 4, so a factor of 10 reduction in the condensate dissolved oxygen. The polisher lifetime, the number of days that they went before pre-coating, increased from 30 days to 90 days, and their air and leakage limit went from 20 to 85 SCFM. So tomorrow, all of this correlated to about 85 to 122 BTU per kilowatt hour reduction in heat rate. So some very significant improvements that we made to this Westinghouse condenser. These changes could also, they were so big, they could also be seen in the data reported to the EPA in their continuous emissions monitoring database. Right here, spring of 2008 was the year that the unit came down and we did all the retrofit work, the turbine work. Was done by somebody else, but that's the outage that all the work was performed in. And you can see here, year over year, a dramatic reduction in unit heat rate. Now, we don't claim that our work did all of this heat rate reduction. The information that we got back from the plant is that 3% was a result of the turbine upgrade, leaving at least 1 to 2% to be responsible from our condenser upgrade. And so, again, to give you just an idea of what's coming up tomorrow, today we talked about how methods that you can use to calculate a target pressure, compare it to your measured pressure, calculated excess condenser pressure. You can do all of that using the bulk parameter methods that we talked about today, the basic condenser monitoring that we talked about today. And you can use all of this to calculate a cleanliness factor. But that cleanliness factor is a misnomer because there's many things that can contribute to reduce condenser pressure and reduced performance. And so tomorrow we'll talk about methods to take a look at each one of these degradation mechanisms individually. And that's the end of the session today. Are there any questions?
Tim, it doesn't look like we have any questions submitted, so I guess we'll just go ahead and call it a day. If anybody has any questions after the fact, feel free to email those to me, or to Tim. You have his contact information as well, and we can start with those then in the morning or tomorrow.
All right, great.
Okay.
Thank you, Randy.
You bet. So goodbye, everyone.